And our next speaker, Chris Vaughan, is on standby to talk about full moon.
Everybody, I feel like this is Freaky Friday because I'm giving a talk about the moon and Michael Watson did talk about the sky this month. So something's funny. But this is the way that the luck went. So here we go. So this talk originated because last fall I had a number of requests for public star parties and limited number of clear nights, and I got into a bit of a traffic jam. And I had a couple of teachers that were insisting that the moon be in the sky. And if you do the math and look at the opportunities, you see that there were times when the moon would set too soon before the folks would gather for the star party and so on. And I realized that I'm going to have to include the full moon nights in my offerings. And on a full moon night, you've got limited options for deep sky objects. You've got some double stars and things like that. But what are you going to show people? How are you going to entertain people for a whole evening if it's essentially the full moon? And so I decided to do a little research and figure out, what I could show people on the full moon. And also, I thought fondly of Blake Nancaro, who's Mr. Anti-Moon guy. And I thought maybe I could convince Blake to get his telescope out and look at the full moon. All right.
Never.
So what I'm going to cover tonight is a little bit about why the moon looks the way it does, and then identify some of the various interesting features that we can see when the moon is full. And then at the end, a few observing tips and some ideas for outreach that you could include on an event like that. I want to stress, of course, because it's the full moon, it's got all those photons, you do not need a large telescope. But if you do have a large aperture telescope, you'll get more resolving power and maybe a little more detail on the features of the moon. But then you have to deal with the brightness, so we'll cover that a little bit more. And I should also say that the moon doesn't need to be completely full for these features to be in appearance. You just need a high sun angle. And the rule of thumb is basically about more than 30, 40, 45 degrees above horizontal, you'll be able to see some of the features that I'm identifying in the talk. So you can plan your event on either side of the full moon. So just some basics. So obviously at full moon, the moon is at opposition. It's opposite. The Earth is between the sun and the moon. And that geometry results in that the moon's Earth-facing hemisphere is being lit by sunlight that's impacting the moon at basically 90 degrees vertically onto the surface. And that produces a lack of shadows, and to some people a boring look on the surface of the moon because there's no topographic effects and shadows and things to make it dynamic looking. So it does look a little flat, but when you look a little deeper, there's more to see. So here's Michael Watson continuing to grace us with his pictures. And at the full moon, the differences in brightness and darkness that we're seeing are not caused by shadows. They're being caused by differences in albedo, or reflectivity, of either the geology of the moon or the textures of the surfaces on the moon. And that allows us to see things like ray systems and volcanic deposits and other things that we'll get into. So a little bit of background, a little bit of history to start with, why the moon got to be the way it is. So shortly after the creation of Earth, maybe within about 100 million years or so of the creation of the Earth, something the size of Mars or so slammed into the Earth and tore off a whole bunch of the Earth's crust, and the heavy parts of the impacting object sunk to the center of the Earth, but the lighter parts and the outer parts of the Earth that were torn off went into orbit and eventually coalesced to become the moon. And this is a neat little graphic that was put together by Emily Lockdewall at the Planetary Society. So what you've got here is if I can get the mouse to work. Got the lunar timeline here. So formation is about 4.5 billion years ago. GA is the abbreviation for gigayears, or billion years. And then we've got the history of the moon going up from there. So from about 4.5 billion years to about the midpoint, around 3.7 billion years ago, we had the period of late heavy bombardment, when there was a lot of extra junk floating around in the solar system and smashing into each other like a giant pinball machine. And the moon was pounded and pounded by these objects. And the larger objects started to produce these large circular impact basins into the moon. So here are the major impact basins labeled on this graph, starting with the oldest and then ending with the most recent one about 3.7 billion years ago, the Oriental Basin. The little curved arcs here are the graphic to indicate how the amount of cratering of the other features sort of is dropping off over time. And then about 3.7 billion years ago, the heavy bombardment came to an end, and something triggered a bunch of lava flows from the interior of the moon out onto the surface, where the molten lava filled in the low areas of the moon and created what we find today as the Maria regions. So if you combine the deep basins with the volcanic flooding, that would combine to give us the Marias that we see today on the moon. And it's not clear whether something started the volcanism to occur at this point in the moon's history, or whether it was happening earlier, but it was just overwritten by the other events. But in any case, for about 700 million years, we have this era of lunar volcanism. And that came to an end, and then we get into sort of the recent history, which is the so-called Copernican era of the moon. And that's where a lot of the major bright craters that we're seeing today were placed on the surface. And note that on this time scale, this represents half of the moon's history, just about in the upper stage here. So here's where we're left with today. We got the moon with a small, meager core in the center, and then a mantle around it, and then a lot of lightweight material that floated to the surface to produce this crust, and probably due to the tidal interaction between the Earth and the moon. And by the way, the tidal locking that the moon exhibits, the single face towards Earth, actually was set up within about 10 million years of formation. It happened very, very early in time. So when that all happened, we ended up with a situation where we have quite a thin crust on the near side of the moon and a much thicker crust, maybe twice as thick on the far side of the moon. And in geophysics, we use a term called equipotential surface, and that's basically what sea level is. If water has the ability to flow around an object and come to its own level, that's called an equipotential surface. And you can see on the moon we have no water, obviously, but the liquid Maria ended up filling in all the low areas and followed this sort of quote-unquote sea level on the moon. That's sort of the way it works. So what we're left with then is this is just a graphic to show some of the major features of the moon that we'll come back to in a few minutes. But whoops. Essentially, we have the white regions on the moon, which are called the lunar highlands, made of one type of rock, and then we have the dark Maria that are flooded with the lunar basalts from the volcanism. Now, as I'm going to be telling you a little bit about where things are located on the moon's surface, it's a good idea to maybe understand the convention of how coordinates work on the moon. It's not intuitive, which you'll see in a minute. So by convention, east is the direction where the sun rises on a solar system body. Okay. North is on the same convention as the Earth, and you can use the right-hand rule for that. So if you curl your fingers and put your thumb up, your fingers are pointing to the direction of the orbit, and your thumb points north. So if the moon is orbiting the Earth or orbiting the sun, that way, north is up. The equator is defined as the circle that's orthogonal to the axis of rotation. And then the central meridian, which on Earth is Greenwich, 0 degrees longitude, is the pole-to-pole circle that crosses the equator at the point that, basically on average, points towards the center of the Earth. And by on average, I mean when both of the lunar librations in up, down, and left, right are zeroed out. So here we are at the lunar equator and the lunar central meridian, point roughly in the center of the moon's near side as we look at it. Now, if you want to think about how to remember this situation where on the ground, west is to our right, but on the moon, east is to the right. So just think of when you're looking at the moon as if you're looking at a map, a road map, where north is up and east is to the right. Simple as that. And if you want to see the actual origin point for the moon, you can look for what I'm calling Wilma's smile. So I see a lady in the moon. I see her hair. Looks like a Wilma Flintstone. So this is the corner of her mouth. That's roughly where the center is. And I think that's where the future lunar Hilton will be built. So we can have the Earth suspended overhead of the pool. And just here's a close-up view of the same location on the moon. If you want to take a look, there's a tiny little crater called Bragg. And the 0, 0 point for the moon is located south of that. You need lots of magnification to see this because that's only 3 arc minutes across. But if you're keen to try to look for that, that's something you can try. All right, so what we end up now is looking at the moon visually. And by the way, you may have noticed that I had icons on the screen indicating the type of visibility of the various objects. So I have an eyeball for visual, binoculars for binocular objects, and a telescope for close-up magnified objects. So the anorthosite is the white rock on the moon. Has anybody read Artemis? Andy Weir in Artemis talks a lot about this mineral called anorthite. But actually the moon is made of the rock anorthosite, which contains the mineral anorthite. And it's essentially a calcium aluminum silicate, which is light and stiff and bright. And as this rock coalesced and cooled off, it grows large mineral crystals. And it's related to the same pink feldspar you have in your granite countertops, the ones you can see the big crystals on. So that's what makes it, that's part of the reason it's very shiny and very stiff. And then we have the basalt, the dark basalt-filled impact basins that range in thickness from about 1 to 4 kilometers. So they'd be about 4 kilometers in the middle, and then they taper off to a thin edge. And they got their names back in 1651 by this Jesuit priest, Giovanni Battista Riccioli. And he, at the time, because everyone thought that those were water features, then he used the theme of weather and water to give the names of the various mare. And the mare, are, as I said, are filled with this volcanic basalt. And if you want to see what the astronauts saw, I brought this Earth basalt, which strongly resembles what you would have picked up on the moon. So if anybody wants to come up and see this piece of Earth basalt at the end of the talk and get a feel for what was collected in those mare. So the mare is actually Latin for sea, and then the smaller features were thought to be lakes, swamps, and bays. So we get Lacus, Palus, and Sinus for the naming. And because the mare are so young and relatively uncratered, they were very benign as landing sites for the Apollo missions. So what I thought I'd do briefly is sort of explain what the Apollo missions were, where the Apollo missions were sent. And you can, at your leisure, then pull out your binoculars or your telescope and look in those regions of the moon. Obviously, you will not be able to see the lunar module or the footsteps or the tracks of the rovers, as some people might think. But it's still fun to look at sort of those areas of the moon and understand, what was going on there. So Apollo 11 was sent to the Sea of Tranquility, and it was mainly sent there because it was near the equator, which was sort of on the plane of the orbit on the trip from Earth to Moon. And it was thought to be a relatively safe, flat region where it was safe for the lunar module to land. And also because the Mare Tranquillitatis is a darker color than the other mare because it's enriched in titanium. And because it had a different style of basalt, they wanted to sample that basalt. Apollo 12 was sent over to Oceanus Procellarum, otherwise known as the Ocean of Storms, another fairly flat, safe site. But in this case, they were hoping to be able to pick up some of Copernicus ejecta. Unfortunately, they didn't get any. Then Apollo 13, which was not able to make it to the moon, Apollo 14 went to the same location, which was in the Frau Maro Highlands, a little riskier, a little bit hillier, and they were hoping to get some of the Imbrium Basin ejecta from when that big basin was excavated back in the early days of the moon. And Apollo 15 was sent up north. It's near Hadley Rim of the Apennine Mountains, where that curved edge of Mare Imbrium is. And they were looking for more complex geology, a mix of the Highland rocks, the Imbrium Basin rocks, and crater ejecta. Now 16, for a change of pace, decided to avoid the mare altogether. They went into the center of the Highlands and the plain of Descartes. And they wanted to hopefully collect some pristine lunar Highlands rocks, which would have been the sort of primordial lunar crust. But they ended up getting a lot of breccias and other mixed rocks from other impacts sort of covering the surface. They weren't really successful in getting that. And finally, Apollo 17 went up there in the sort of upper boundary between Serenitatis and tranquil lattice. And they were trying to get crustal rocks plus mare basalts and other things as well. And actually, they ended up collecting some pieces of the ejecta from Tycho, all the way up there in the airport, about 900 kilometers. So this is the situation we have on the moon. We've got this sort of layered topography or layered structure, stratigraphy, with different contrasting colors to them. So we have a sort of ignore the colors in the diagram, but essentially this white lunar crust, and then it's filled in areas with this dark colored basalt mare. And then as the lunar sort of surface matured, it gets subject to weathering and alteration. Not by due to wind and water as we have on Earth, but because of micrometeorite impacts, cosmic rays, hot-cold cycling, and so on. And that sort of darkens the moon. So you start with the sort of pristine white lunar crust, would become kind of darkened after weathering for a time. And that would sort of cover as a veneer over everything. Then if you get an impactor coming in and hitting an area where the lunar highlands are, it would excavate and expose the fresh white northocite rock and partially cover up sort of the medium gray regolith over top. So you can sort of get a bright floor crater and maybe a bright halo. And it can also, of course, spew some ejecta onto the dark areas and make these white light color rays. Or you could get an impactor that comes into a maria, which exposes or punches through the regolith, then exposes the fresh basalt. And it can toss the ejecta around it, but it can also toss it onto part of the highlands, and you get these sort of contrasting situations. You can have bright rays, you can have dark rays, and you can even have situations where the impactor will come and punch through both layers, and so you get a white crater floor, and then you get some black, and then you get some white ejecta around it, so you get all these cool halo effects. So here are the prominent ray systems that you can sort of just look at with your naked eye. I'm not going to go into all of them in detail, but most of the areas of the moon have them, and they're very prominent during times of full moon because they have zero topographic relief, and they're enhanced by the direct sunlight on it. So some of the major ones especially are Tycho near the bottom, of course. The rays on this system are about 1,500 kilometers long. And notice that the rays are not symmetrically radiating. There's actually a zone around here and an empty zone here. And that's an indicative of the direction the impactor came in from. So the body that created Tycho must have come in from lunar west and then spewed all the ejecta towards the east, north, and south. Likewise, Copernicus has a radial ray system, so it was more of a vertical impact. And the rays of Tycho are sort of long and very straight. Copernicus ones are a little more ragged. And Copernicus, by the way, is about 108 million years old. We know that because we've had age dating of the samples returned by the Apollo missions. And the Copernicus region was created about 800 million years ago. And then you've got Anaxagoras at the top, which is about a few hundred million years old. And we have Kepler down here, which is a smaller ray system. And it's less than 800 million years old because it overlays part of Copernicus' ray system. So you can sort of create the history by looking at how things overlay on top of one another. So zooming in a little bit, let's get into some detailed objects for you to now drill down on. So the first one we're going to look at is a ray system called Proclus, which is near Mare Crisium. And in a telescope, you can really see that Proclus has one of these asymmetric ray systems where the material only went one direction. And planetary scientists have modeled the situation and realized that the impactor was probably coming in about 4 degrees above horizontal. They're almost a grazing hit. So that's a cool one to look at. Next one is Messier. The Messier is a really neat one. So Messier looks like a comet. It's actually a pair of impactors hit together near one another and generated these long comet-like rays. So again, this is an impactor that would have come in from the lunar east at a shallow angle, probably at about 1.7 kilometers per second, and generated these long rays. You can also see that there are other rays radiating north and south. So I don't have the explanation for exactly how all of that is created, but It's the way that planetary scientists can unravel what's happened on the moon. This is a specular reflection this is from an Apollo mission, and this is basically the sun reflecting on the moon, just giving us that funny bright patch. Dionysius is close to where the Apollo 11 landed. You can see it even visually. It's that little bright white crater. Zooming in on it, you can see that it's excavated the pristine white. It's got a white floor because it's excavated into the lunar crust. And it's actually punched through part of the Mare from Mare Tranquillitatis, and it's spread the rays that are now black because the basalt has been distributed around the crater. So you've got these dark ray systems around it instead. If you look at Copernicus near the full moon, where the sunlight is at a high angle, it really enhances the fact that you've got terraces around the edge of the crater. And the terraces are basically due to avalanches slumping on the edges of the crater long after it was formed. You can also look at the dark craters. The dark craters are kind of mini Maria. They're essentially craters that were generated, and then the energy produced by the impact has caused the lava to well up and flood the interior of the crater. Both Grimaldi and Plato are two examples of dark craters. Once you're on the lookout for them and you look around, you can start seeing the bright little white crater floors everywhere on the moon. And those are all the youngest craters on the moon, the sprinkle-like stars across the surface. All right. So here's a cool one. This is called Cassini's bright spot. It's north of Tycho, and it's located just east of this crater called Hell. And it's this little spot here. Cassini observed this and claimed he saw clouds. No one was able to actually, confirm that. So we don't know how much wine he had or whatever he was doing. But it's a fascinating area. It's one of the brightest spots in the entire moon. They think it's about 100 million years old. And you notice that the fan is about a 90-degree angle, and it rays towards the east. So again, whatever caused this has been arriving from the west and generating the rays to the east. If you're doing a search, don't confuse Cassini's bright spot with an actual crater named Cassini, which is near Marion. Reiner Gamma. This is another really interesting one. Reiner Gamma is over in the west. So this is a feature that has zero topographic relief. It's more like a stain on the top of the Oceanus Procellarum. And the thinking here is that there's something buried in the moon's crust that's generated a stronger local magnetic field. And the local magnetic field has acted like a shield to reduce the amount of weathering on the Mare surface. So it's actually allowed the original lighter colored Mare surface to be a brighter color than the darker weathered Mare around it. And some people claim that if they study the shape of these sort of swirls, that they can almost sense the shape of the magnetic field that surrounds it. So that's another one you could try. Dark halo craters. So back to Copernicus for a minute. Copernicus is surrounded by a whole bunch of these little dark halo craters. There's one here, and you can see that they've got white bottoms because it's penetrated into the lunar crust below the Mare. They've got black halos from the Mare material they excavated, then they tossed around to the edge of the crater, and then they sit on top of the Copernicus ejecta. So you've got sort of three layers of sandwich there. So those are visible in a reasonable sized telescope. Alphonsus. So Alphonsus is an example of volcanic deposits. So I don't know if you can see it here. You can see three little black spots in a triangle. So those are visible in maybe your naked eye, but certainly in binoculars. If you zoom in, you can see that the crater floor has these three dark stains or dark smudges with little calderas in each one. And these are basically like cinder cones on the Earth. So pyroclastic volcanic deposits loaded with carbon dioxide has come to the surface of the moon, exposed to the vacuum, and then violently erupted at the surface of the moon and stained the area around the volcanic eruption with these dark deposits. So this is not a high sun angle view, but this is a high sun angle view that's taken by Gary Saronic. You can really see the central peak in the center and then these three dark volcanic deposits. So that's sort of near the center of the moon. Up near the north
eastern edge of the moon, we have the crater Atlas that has another one. So Atlas has a pair of them. There's one here and one here. And I've seen these in my telescope, so I can assure you that you'll be able to see them for yourself. And next to Atlas, you've got the Hercules and its fresh subsequent Hercules G that punched into the original Hercules, and it's got that bright, white, fresh flow on it. Final feature that you might want to look for is to see if you can pick up any of the colors on the moon. The moon is not black and white. There are places on the moon that have staining and various colorations. So particularly the area to the west and north of Aristarchus, there are these sort of warm colorations, tinted colorations, and the missions have actually detected sulfur compounds in the area and detected radon-222 emissions. So there's something unique about the geology in the area. So that's basically it. This is sort of your list of objects to check out next time you're doing a look at the full moon. And just some tips. So, as I said before, you can look at the moon, the full moon, days before and days after full. The sun needs to be high, but not vertically onto the moon's surface. A large aperture telescope is obviously not needed, but if you use it, you'll get more details. You'll see more details on the moon. It's just that you'll want to deal with the high brightness factor. So that's where you bring in, say, a neutral density filter, or maybe a variable polarizing filter, just so you can dial the brightness of the moon's image up and down. Enjoy taking smartphone pictures. The moon is the easiest object to take pictures of, so it's something you want to try. And when you're trying to find the objects in the moon, you want to use charts that are oriented to match the optics in your telescope. So it's fine to use paper charts to match your binocular view or your naked eye view, but if your optical train is flipping or inverting the image, then you can find charts designed to show you the moon in the same fashion. Or you can use your app settings and adjust the app to show the view flipped or mirror imaged. So here's just a few ideas that you can do if you've got a group of people looking at the full moon. Observe the special features, show them the special features I've demonstrated tonight. Take a look at the lunar vibration and how the positions of Grimaldi over here and Merecrisium are changing with respect to the edge of the moon's limb. You can ask what pictures and what shapes they see. Me, I see Wilma Flintstone. I don't know what they might see. Have them bend over and look at the moon upside down. Michael's going to a southern hemisphere. The moon looks weird when you're down there. It looks upside down. Teach them how to cover the moon with your pinky finger. Even though the full moon looks enormous when it's rising, you can still cover it with your pinky finger. And of course, you can have them take pictures. So here are a few resources that I used for the preparation of this information, this talk. The photographic moon atlas is a great one because it's full of the actual images that you would see through your telescope. But a number of these are free or very inexpensive. The Lunar Map HD app here is a nice one because it allows you to have the charts on your smart device, but you can flip it and invert the view to match what you see. You can control what features are labeled and the amount of density of labels and things like that. And this Lunar Field Atlas by Fred Days is kind of a successor to the Ruckel's Moon Atlas. It's a similar style, but it's a free download, and you can actually pick what version you want. You can have regular moon, inverted moon, flipped moon. He's got it all prepared for you. So, hopefully next time, Blake, you'll pull out the telescope and look at the full moon. No? Yes? You don't have to admit it? No witnesses? So the next full moon is March 31st, Blake. And set up your telescope and take a look. Thanks a lot. Questions?
Hello.
Hi.
Two things occurred to me. What strategies are used to assess the actual time frame when these initial contacts with the moon were made? For example, you'll show a crater. How do we know when that happened? And secondly, what are some of the more later ones?
So when was the crater formed?
Yes, and how do we know that?
So essentially the way that you build up the history of the moon is by trying to see superposition. What event overrode or obliterated something underneath it? And that must be the freshest event. So by sending astronauts or robotic probes to the moon and collecting samples, and you can take a piece of rock that you've got brought from the moon, and you can radioactive age date it. So you can tell quite precisely when it was crystallized, when it was formed. So the Apollo astronauts were able to collect, albeit only 6 places on the moon, but they were able to get accurate ages for those parts of the moon that they visited. So we know that Tycho was created 108 million years ago because we've got pieces of the rock from that event. And then you know that if Tycho was spread ejecta over top of another crater, then that crater must be older, and so on and so on and so on. So it's complicated, and it takes a long time to work all this out, and it's why we need to go back and do more of this. But that's kind of the way it works, if that's clear.
And the second part of the question, what was the most recent impact that you know about?
Well, in terms of large impacts, Tycho is basically the most recent large impact. Every once in a while, somebody will report that they've seen a fresh impact on the moon. Mm-hmm. You can happen to be looking at the moon when it happens, but they're not generally very large because there's not a lot of large objects hitting them right now. They're mostly small objects. But that's one example of a fresh one. So if it's bright, it's likely fresh. That's the rule of thumb.
Thank you.
That's good. Hang on a second. I'll get you the mic.
It's a related question, but you indicated that there may recently have been impacts on the moon. Are there impacts on? Are things hitting the Earth?
Well, we have Chelyabinsk and other objects of different sizes hitting the Earth all the time. Most of the time, they're small objects that burn up in our atmosphere. But sure, every once in a while, something reaches Earth. I mean, meteorites are objects that have slammed into the Earth and hit it. Sure. Yeah. But not generating, craters that are kilometers across. That's not happening. Oh, I think you could get a fresh meteorite crater that could be a meter across.
Has anybody been hurt or any property damage?
Not really. Every once in a while, there are reports of a meteorite hitting a car or something like that. But generally, even though a lot of us around, the Earth is pretty big and we're pretty spread out, so it's not too dangerous. But yes, it does happen for sure.
So I'm a little more curious about the brightness of stuff that you talked about, because as far as I know, the cliche is the moon is reflective as a parking surface, but obviously it's quite a bit more variance in the brightness. So are there ways of comparing in your mind, like how bright the Highlands are, relating it to something on the Earth?
Well, there's the Maria right there. So it's not very bright. This one's a little bit weathered. There's a little bit of, you can see that it's a little brown. But come up and take a look at this. That'll give you an idea about the Maria. Off the top of my head, I don't remember what the albedo of the Highlands are. Do you happen to know?
The overall albedo of the moon, it's actually really interesting, is 18%. It's one of the darkest objects actually in per sort of unit area in the solar system, although it doesn't look that way.
Yeah.
And I think that the Highlands are about 3 times the brightness of the Maria.
Yeah. I was going to say like 5%, 25% albedo, something like that. So think of a paved parking lot. I mean, on a sunny day, it looks sort of bright, but it's actually dark, the material stuff. Yeah. Thank you.